part, you know. So I don't know. Okay. So let's see. It looks like I have that selected. So I obviously copied that and moved it down to here. And so let's see. So let's see if I can get this kind of straightened out. Okay, so I got my two. So I'm kind of reviewing actually for myself. I got my two uh, problems here, each with their own datums. And then I went over here and I put the datums in for the two, the mass A and the mass B at the initial state or the initial time. And then I decided that was going to be one. And if this is one, then this thing rolls down the hill. I always think it's interesting in this book. He has these little shadows that indicate that that's the way things should move. And so it always gives you kind of a, wait, one goes up, one goes down. And look, there's the shadow over there. And it's just a little shading. You notice that throughout the book, he has those. It's very funny. Okay, so then I got those, and then I got the final H's, the 6. So this one went up 6. I hadn't done the friction yet, and I just I just left the hang on. I just left the energy part. Was it this color? No, it was purple. I just left the energy part in there like that. So let's complete out the rest. So I'll deal with the friction in a second. So the first thing I'm going to do is I'm going to try to move all this junk. Oh, well, there's nothing there. So that's 0. This is 60. I don't know what. I don't know what that is. Oh, 108? Okay. Okay. So then I move the 60 over to here. And then I get this, which I'll deal with in a second, equal to, okay, now I got to make sure. He said one was 10 pounds, right? Okay, B was 10 pounds. Okay, so B, so 1/2. What was A? Wait. Oh, wow. Okay, it was 60 pounds, and this was 10 pounds. So the mass, so the weight of these things is equal to mg. So therefore, the mass is equal to the weight divided by g. And in this case, that's 32.2. So you run down here. Okay, so I'm looking at A. Gosh, I've already forgot. Which one was A? Is it the heavy one? It was the heavy one. 60 over 32.2. B, I could say 2, but I'll just say A squared. I'll go ahead and put the little 2. Plus 1/2. It was 10, right? 32.2. The B2 squared. Now, there's a relationship between these two. And there's also friction. So I've got to do one of these first. Maybe what I'll do is I'll do the friction and then I'll deal with this second. So let's look at the friction. I'm going to do, since I already have this, I'm going to do it this way. I'm going to copy this picture. The friction only exists in this one. There's no, I guess technically you could have air friction here. You could have some air resistance, but it's not rubbing against anything. We already found the frictional force was 9.6 pounds. So here's your 9.6 pounds, and it's moving this way. So since that's the case, Um, I meant to put the summation. Dot S, there's only one thing. Now, if there were multiple frictions, like if this had a friction too, it would be included in there as a sum. So you would have, the 9.6 times the distance it slid down, which I think was 3, or maybe it was 6. No, it was 3 foot. So it moved down 3 foot, but they are both going in different directions. So if I take this vector, oops, that's the wrong thing here. Take this vector and dot it with that vector. The angle between them is 180 degrees, and the cosine of 180 is equal to -1. So in fact, this becomes minus. Now, if someone were pulling it down, then that force in this direction would be the same, and it would be positive. It would be adding work to it. So since it's taking it, since it is slowing it down, it becomes minus 9.6 times 3. Okay, so now I need to address, so I hadn't done this yet. So here, let's write all this down, because I'm going to use that thing to calculate it in a second. 9.6 times 3 equals 2. Okay, so I got all that. Now I got to figure out the relationship between VA and VB. But the second thing about this is they're squared. So if VA was negative or positive, it doesn't matter. It's just the magnitude of it. So I go back up here somewhere, right here. So this is the relationship between those two velocities. So in fact, it does not matter whether I choose that to go down the plane like I have. So I could just say this is going to be the direction of VA and this is the direction of VB. That doesn't matter. It just matters that 2 times VA plus VB equals 0 if I've taken this as the direction. So now what I'm going to do is, instead of trying to remember that, because I have a short-term memory problem today, I'll do a copy and I'll go all the way back down here and just sort of drop it maybe right here. And that's how they relate. So I can choose whichever one I want to do. I'd rather really not have a fraction. So what I'm going to do is I'm just say VB is equal to minus 2VA. Instead of VA is equal to 1/2 VB, I'd rather not deal with the fraction here. So I'm just going to deal with that one. And so in here, I'm going to extract that. And because of this, I'm going to write the 2. Now I can put the minus sign in there. Doesn't matter because it's going to go away because of the square. So then what I've got is 1/2 60 over 32.2 VA squared plus 1/2 10 over 32.2 times 2 VA squared out like that. So then I can combine these terms and say 1/2, and this is where I'm going to use that picture thing. Okay, and then plus 1/2 10 times a 4, because I'm going to pull that 2 squared out. And VA squared. Oh, so I can just combine it all together. Or maybe I want to take the picture there. I don't know. Who cares? I'll just combine it all together. VA is equal to, as long as I have enough space above it or below it, I can take the picture. And that would be 108 minus 60 minus 9.6 over 3. Out of curiosity. Okay. Where did it go? Did I move my stuff around? I think I moved my stuff around. Oh, it was on the first page. There we go. I was using it enough that I thought I should put it on the first page. Just out of curiosity, that becomes 19, but I can just leave it in there. I just wanted to see this number became 19.2. Plus 1/2. This will be a testament to see if it can do something. I mean, I'm trying to write to the point where it's visible. Okay. Did it copy the right? It did. Huh. So it says 3.516 is equal to VA. So I've been moderately surprised this thing tends to copy, or the picture I take tends to show up the right way, with a few exceptions. Okay, so let's see, we solved that one. We solved this one. But again, my approach, okay, this one had multiple masses, so you have to sum all those. So what you have to kind of do in a generic sense, so here, I'll put a slide down here. Generically, it kind of looks like this. Sum of all the masses, sounds weird, well, how about we do this? How about I don't know, I equal 1 to the number of masses. Of all the energy states, MGHI plus 1/2 MVI squared plus 1/2 K delta I squared. All of those, so all the potentials, so this is essentially the energy at state 1, or you might say time 1, and plus the sum of all the forces applied between state 1 to state 2. So this would be added energy or taken away energy from friction. And then, so this would be, now this is funny, but here, I'll just say this, do a copy, and then go over, I think it's at the top, that right there equals to all the energies at state 2. So it's, we're in the business building, so it's kind of like accounting. You take the energy you started with, then you either add energy, E added, or E taken away. And then you end up with, it's just basically energy accounting. Energy just doesn't disappear, so it's that simple. So that's kind of the generic form of everything. So let's see. That is the, okay, wait a minute, 7, 8. What happened to the, oh, here we go. Is this it? All right, there we are. Okay, so I think we did this one and we did this one. Is there anybody else that might be intriguing here? These two are replicas of the other. However, I should do 14, 20, 21. Let me see if I want to do 14, 21 or however, wait a minute. Excuse me. You know what? Here's some springs. Those don't have springs. I'm going to do some with springs. Those don't have springs. So one of these three. I'll do the first. I'll do this one, the K21. I'm sorry, K22. Okay. Should I just keep going down? Why not? There's the problem here. Escape, do that here. Here's my new problem. It says in a second. Here's the thing. Okay, so it says it's a 25-pound block, has an initial speed of that 10. When it is midway between the two, after striking the spring B, okay, it rebounds and slides across the horizontal plane towards spring A. If the coefficient of kinetic friction between the plane is 0.1, determine the total distance traveled by the block before it comes to the rest. This is a trick problem because there's only one case that would be an oddity, and even then, it's a little bit of a strange oddity. Here's the one oddity, that the block ends up being stuck with a spring slightly compressed, and there's enough friction. In other words, if I do a balance of forces, this force from the spring offsets the static friction. That is possible, that it could bounce back and forth and then get stuck right there. But we'll first operate on the premise that it doesn't do that. And if it doesn't do that, then every time it hits that spring and compresses it when it comes off the spring, it's basically just lost the energy due to the friction. So it's going to give you back whatever that compressed amount, it gives you back that energy. And so it just bounces back and forth. So essentially, the answer is, okay, wait a minute. So this thing is how much? 25 pounds. This means if the block is moving this way, it doesn't matter, N's always going to be 25. So the friction force is going to be 0.4 times 25. What is that? 0.4 times 25. 4 times 25. Here. I hate to do that, but yeah, I was about to say, I think that's what it is. So the force of friction is 10. So it's as if this block is starting there with 10 feet per second, and it just slides down here across this frictional force until state 2. Okay, we'll call it state 1 and state 2. State 2, the velocity is equal to 0. And the spring just compresses and decompresses. So it's as if whatever energy was put on that spring, it just gives you that right back. And so in essence, on the left side at state 1, your energy just becomes 1/2 mv squared. And that's 1/2 m would be 25 pounds over 32.2. V would be that, equals to the amount of distance it went and the frictional force of 10 pounds. Okay, and then so this would be a minus the frictional force of 10 pounds times the distance equals to the final energy state here at 2 is it's lost all of its energy. So in essence, D would be equal to 1/2 25. You divide the 10 out of both sides, you just take away 1 there, times 10, and that's the distance. So it's kind of a trick problem in a sense. They're not trying to trick you, I think. Maybe they are, I don't know. So it moved 3.88 feet. So every time it hits that block. Now the key is, if you really want to be, I mean, there's quite a detailed thing. By the time it reached this speed, then at a certain instant later, it compressed that spring. So if you measure from here, you would measure all the way to there. And then what you would do is you would measure all the way back to the point where the block slightly compressed this one. And then you would measure back to a certain distance here. So if you consider this to be 1, it's not, and this is about 2, then you would almost return back there, but there's these small compression distances. The key is, I think, it does not end up sitting against the spring. So in other words, it could sit against this spring slightly compressed, with a friction force like this, but I doubt that that would happen. Because if you compress that, I mean, if you think about it, that thing is 10 pounds. The friction force is 10 pounds. With a friction force being 10 pounds, there is a possibility that that friction force would be K times the delta of the spring, and K's 60 per inch. Okay, 60 pounds per inch. Okay, so 60 pounds per inch, 144 inches per feet. So I doubt that it's going to sit in that case. So we'll go on to the next one. That one was kind of a trick one. This one, let's do this one. Here, I'll just copy it first. And then, today is Wednesday, right? Isn't today Wednesday? Okay, so Friday what we'll do is we'll go to impact and do a set of problems. And then essentially, that's all you'll be tested over. So I'm going to give problems on energy and impact. What I'm going to do, I'm going to give the energy problems in homework, whatever. I'm going to go ahead and make that due the last day of classes, and then do the impact last day of classes, and then I'll do the final. I'll have to sit around. That one will take some time for me to patchwork that together. Okay, a 5-pound cylinder is falling with a speed of 10 onto the platform. Determine the maximum displacement. The spring has an unstretched length of 1.75. So here's your key. All your energies at state 1 would be 1/2 mv, and I'll go ahead and put a subscript. State 1 plus mgh state 1 plus 1/2 k delta at state 1. I'll go ahead and include the F dot S's, but there are none. There's no friction no friction, and no added forces. And what I end up in is state 2. And the state 2 is determine the maximum displacement of the platform caused by the collision. Okay. So he does say neglect the mass of the platform and spring and the energy loss during collision. So these have no mass. So if you did have a 1/2 mv squared, they would be 0 because of the mass. And so what you're going to have is MVA2 state 2 plus MGH state 2 plus 1/2 K delta at state 2. So again, we're starting with the energy in state 1, is that, adding or taking away and ending up at the energy at state 2. The convenient thing is, and I don't know, I guess we'll just do it like so. I'll just pick, well, I'll do this. I'm going to pick the datum that would be the datum of the deflection of the spring. So this is going to be, or do I want that complication? No, I don't want that complication. I'm just going to pick this. Because if I use that, then inside one of the terms, I have an extra. I mean, it'll give you the same answer either way. But, okay, so my initial energy due to kinetic energy is 1/2 m, which it's a 5-pound cylinder. So that would be 5 over 32.2. The velocity initially is 10 feet per second plus mgh. M and G going together would be 5. H is 3 feet because I picked my datum right there. And then the initial compression of the spring happens to be, it's unstretched at 1.75. So this means it is 0.75 squared already stretched. So there's already energy in that spring. Then the final state will be there is no velocity, 0 squared. MGH, now this time there's going to be a slight compression here, which from the datum standpoint is going to be the weight of the thing times this time minus delta, because it's below the datum, and then 1/2 K, which is 400, and now the compression is delta plus 0.75. So unfortunately, either way I would have done that, it would have been buried in there. Just anyway, it doesn't matter. So from this, I get 15. From this other, I get I get 7.76398 plus 15 equals to, okay, now I've got the complexity of dealing with this, which is a minus, oh wait, I forgot that term right there. Let me put that one in there too. Let's see. Okay, it's going to get mad about that. So I'll shrink it together and do that. Oh, okay. Plus 112.5. So there's quite a bit of energy in that spring already. Minus 5 delta plus, okay, it's that squared. This will be interesting. I wonder if this thing will solve a quadratic equation. So that will be 200, and this will be delta squared plus 2 times 0.75 times delta plus 0.75 squared. Okay, so what I'm going to do, I'm going to add all these terms on the left real quick. Okay. So I get 135.26398 equals 2. I still got the minus 5 delta plus 200 delta squared plus, okay, 2 of those is 1.5 delta. And then just out of curiosity, let's see what happens if I do that. I wonder if it will let me do that. It's going to get confused. Interesting. Okay. Okay. So I'm only intrigued at trying to figure out now what this is. So if I take 200 delta squared, so I'm going to try to make that, do my handwriting fairly decent, plus, okay, 1.5 minus 5, that'd be 3.5. And then I got, wrong. That would be 200 times, okay, so 200 times 1.5 minus 5. What is that number equal to? I'm sorry to bore you through this, but I'm entertaining myself. So it's 295 delta. And now I got to take this term, which is 200 times 0.5625 minus 135.26398. He will not like that. 26398. Okay, so let's get rid of that, and maybe I can get this other part figured out. Uh-oh. No, it didn't get it. Huh. So it says 200 delta squared minus 295 delta minus, I get 22.76398 equals 0. I am now going to see if this thing can solve a quadratic equation. So the first thing, well, it says it's solving the quadratic equation. Huh. So it did it. Okay, so it says delta is either or minus 0.0735 or there you go. So it can't be the minus because it can't compress it that way. And so there you go. I'm assuming that this thing is solving, all the terms correctly. So that's essentially it. I mean, I don't know how many other problems you can do that they just get kind of monotonous after a while. So I'll assign a few so you can get a little practice. Then, it's funny is he's got a set in here and then a set down here. The first set has friction involved. The second set does not have any friction. Okay, it goes through here. That's pretty much it. So maybe what I'll do is spend about 5 minutes, and that's all it would take, setting up the next chapter. And it's just simply this. If you look at the way, F is equal to MA, people have talked about that for years, but actually, and when we became an engineer, you had to put that in there. The actual equation is this. And so then you just have this, and you can integrate both sides. And so this would be at T1, and this would be MV evaluated at T1, and this would be T2, and this would be MV evaluated at T2. That's the entire chapter. The only things you deal with is you might have multiple masses instead of just like one mass being pushed on. That's how you'll start. Then you'll go to the point where you might have one mass ramming into the other. And then we'll go to the point where energy will be lost. So at first we'll deal with all the energy's lost or none of the energy's lost. Then we'll deal with, you drop a ball, it's dropped from this height, and it only returns up to here. So you lost energy here. And then we'll deal with that. And that's pretty much it. So there's only a few things in there. So that's all I got. Which is good because that's all, I guess that's all the time we have. And now I've got to figure out the parking situation and when they were going to come